Good morning, everyone. Welcome to the Net Zero Committee meeting. We'll hang on a couple of minutes whilst we get people online. Good morning, everyone. Thank you for joining us. We'll give it a few more minutes just for people to come online. Okay, whilst we're waiting for more folks to join us, I will just go through some housekeeping notes. So it's a webinar, so your microphone and camera will be kept turned off during the webinar. Please use the Q&A function to ask any questions. It depends on your version of Zoom as to where this may be, top or bottom of the screen it could be. The questions when asked are not visible to all attendees. However, the chat function is visible to all. So if you wish to chat, then please do. We will be recording this presentation and it will be made available on the website afterwards. So some upcoming events. Tomorrow, our first real in-person conference, the Well Decommissioning Conference, happening at TECA, the Exhibition and Conference Centre here in Aberdeen. So it's not too late to get tickets for that still. It'd be great to see people in person. And then next month we've got Seismic and DevX. Please go to spe-aberdeen.org or for more information, but also follow us on social media for the latest updates on other meetings. Our next technical meeting, 4th of May, YP Simplified series, the energy industry in 2022, Transition and Action by Brenda Wiley. So again, go to the website, sign up for that one, and keep an eye on the website and social media for the next Net Zero Committee meeting as well. The Net Zero Committee is part of SPE Aberdeen, but falls under the umbrella of SPE International's Gaia Sustainability Programme. So co-hosting with me today, are you there, John? I've got John Butler, who is involved in SPE International, in hydrogen in particular, and involved in SPE Gaia, and he's he'll be joining us to help with the Q&A after the session today. So he's going to be here helping with us with that today. So without further ado, I would like to introduce our speakers and our presentation today. Miniaturized methane sensors and drone technology for accurate identification and quantification of emissions. So Dr. Peter Evans of BP has kindly agreed to present on their experiences of this technology. And we're going to start off with Mike Sutcliffe from Seekops, who's going to give us a brief overview of Seekops and the technology first before we hand over to Peter. So over to you, Mike.
Great. My name is Mike Sutcliffe. I'm with Seekops. I'm in Aberdeen and I'm the Business Development Director here. So Seekops is a company based in the US, based in Texas, and we provide methane sensor technology for measuring methane emissions around all types of sites. Just move on to the next slide, please.
Yeah.
The company was actually originally formed about 5 years ago. The technology that we have developed was originally developed by NASA and used on the Mars rover missions, and then the company Seekops was formed, and over the last 5 years we've further developed our technology for methane detection and quantification to make it a robust and accurate sensor technology for measuring methane emissions. The sensor is very reliable, it's very lightweight, and because of its size and scope, it can be deployed on a drone. And we typically deploy it on a rotary drone because of its lightweight. You can see an image there on the slide. I've actually got a model here of it. So this is the real size of the sensor, and this is attached to a standard drone and deployed in that way. We also have a type where it is deployed on a fixed wing drone, typically flying much longer distances and typically around offshore installations. But this is the standard sensor that we deploy on a rotary drone. There's a few figures there, a little bit about the specification, but essentially it is very precise. It can measure down to parts per billion concentration of methane in the air. It contains all the power, telemetry, and memory storage that's required, as well as the actual sensor itself. The sensor is based on a tunable diode laser technology, which is deployed in the blue section of the diagram of the picture you can see there. It has proved to be very robust and reliable, and what we are able to do is measure the methane concentrations around the sites and then use that data to create a total emissions from that site. Next slide, please. So this is deployed both onshore and offshore, and around a typical onshore site, as you can see here, these green lines shows the flight path that the drone would fly all the time collecting data. We're collecting data 10 times per second, 10 measurements per second during flight. So on a site like this, we may have tens or even 100,000 data points that we use, each one an individual methane concentration figure. And using that data and also the wind speed and direction that we're also recording during the flight, we're then able to, using our algorithms and our modeling, to quantify the emissions, the methane emissions that are coming from a particular site. And also within the site, with the wind direction, we can also localize where those emissions are coming from on the site. So a typical flight around this, can be done in a relatively short time, maybe an hour's flying or a bit longer, depending on the size of the site, but a typical flight is less than 1 hour. Next slide. We also deploy this offshore, on offshore installations. We can deploy either from the helideck or from a vessel nearby. And similarly, we fly a grid arrangement around the asset, taking data measurement points. Next slide. Another way of deployment is on a fixed wing. In this case, we've been working with a company, FlyLogix, who are aviation specialists for doing beyond visual line of sight, so long distance drone flights using a fixed wing aircraft. And we deploy the sensor within the wing of this device, and we fly typically circles around the offshore assets to take data points again. And similarly, we do modeling on that data to quantify the emissions that are coming from an offshore installation. Typically here, we're flying about 250 meters from the asset to taking those readings. The deployment of these is from land, so these are flying from land to the offshore installation and back again. So there's no requirement to mobilize people or equipment offshore to the installation. Next slide. So thanks, that's just a very brief introduction. I'm very grateful for Peter Evans from BP, that he is going to present some of the data from BP flights that have been performed and data. One of the great things about Seekops is that we've had great support from operators and BP in particular in developing this technology and bringing it to the current state that it is, in terms of trialing it and piloting it to where we are today. So thank you. Over to Peter.
Excellent. Thank you, Michael. If I just flip screens so we can put the BP presentation. And hopefully we should now be in full screen mode, and I'll get talking. So thank you so much for people inviting me here to speak with you today. I'll give you basically a more in-depth exploration of what we do with these sensors, building upon the summary that Michael gave a moment ago. But before we do that, it's worth spending just a moment or two just reflecting on why we're doing this before we get into the sort of technical nuts and bolts of how we go about it. And I'm mindful that it's probably a fairly mixed audience on this call today, from people who are probably subject matter experts in this area in their own right, through to a more general audience. And you know, when we're talking about methane, this is very much a world in which one molecule has two names. When we're talking about energy demand and the energy transition, we tend to talk a lot about natural gas. And then when we're talking about greenhouse gas emissions, we talk about methane. But of course, the two things are essentially the same thing, because natural gas is predominantly methane. And particularly with this audience, I think it's important to recognize that natural gas has a critical role when we talk about the energy transition, and almost unique role that it plays within the energy mix in providing the energy density and the flexibility that the world needs to sit alongside some of the other energy technologies which are coming to the fore these days. But in doing so, we also have to recognize that methane is a greenhouse gas. It has a higher global warming potential than CO2. It depends on which time frame and which research you look at that, but somewhere in the region of 25 times more potent as a greenhouse gas over a 100-year time scale, which is what we use for reporting purposes, and that's certainly the value that bodies like the IPCC use. And therefore, methane matters when we talk about greenhouse gas emissions, and particularly so when we start digging into the surface of where methane comes from. And methane in the atmosphere comes from a whole host of different natural sources and mankind sources. And around a fifth of the total methane in the atmosphere today has its origins in oil and gas production and use. And because methane is more potent than CO2 as a greenhouse gas, that equates to about 1/5 of man-made global warming is associated with methane. This is where it then differs somewhat from when we talk about carbon dioxide, because methane is a reactive gas. It has a short residence time in the atmosphere because it breaks down through a variety of natural processes. And therefore, by tackling methane, it has a critical role in addressing climate change. And in particular, it has a critical role in the pace at which climate change projections play out, and making early interventions in terms of methane emissions will have a big part to play in that in the coming decades. Now, this isn't just an oil and gas issue. Methane comes from a variety of man-made sources, from landfills and agriculture. But as an industry, and it's mostly industry people on this call today, we're very different compared to those sources, in as much that, yes, this is one of our emissions, but this is also our product. And we have the knowledge and the capability to bring down our emissions in a way that not necessarily other sectors can as quickly. So the eyes of the world very much look to the oil and gas sector in terms of what we can do. And we see that in a whole host of different commitments that have come out in recent years. You could do a version of this slide for pretty much every oil and gas major around the world. But if you picked out particular things which have happened in the last 2 or 3 years, well, feels like a long time ago now, but back in early 2020, when BP went through probably its biggest restructuring in history and set itself on a path to be a net zero operator, it set in place a target, which is called AIM4. It's one of 5 targets around moving to net zero and one of 20 targets around BP's move towards an integrated energy company, that said that we would install methane measurement systems on all of our major oil and gas processing sites by 2023, starting to feel quite close, and then use that to drive a 50% reduction in our methane intensity. And that we would influence others to follow similar targets. And at the time, we set a methane intensity target of 0.2%. If you look at things like our sustainability report, you'll see that we're currently significantly lower than that already. But that's on a calculated basis. That is a methane emission intensity based on a whole series of assumptions and engineering calculations that go into our reported values. And what we're now doing is moving to a measured basis, and why that matters we'll pick up in a moment. But it doesn't exist in isolation. There are other commitments that have appeared around the world as well in terms of where we're heading to. And possibly the most significant of those was a UN-led program called the Oil and Gas Methane Partnership, or the second version of it, to be more precise, known as OGMP2, which at the back end of 2020, so about 6 months after BP's own commitment, it set in place a commitment to install methane measurement into companies' reporting. And that covers about 30% of global oil and gas production and the full gas value chain. Building on the 2020 activities, by the time we get to 2021, and events such as COP26 held in Glasgow, we're seeing the stakes being raised further. And we have things like the Global Methane Pledge, and this is now governments making pledges, and this is about a 30% reduction in methane emissions by 2030. Moved forward to this year, and we're already saying sort of industry groups like the OGCI, the Oil and Gas Climate Initiative, laying down objectives to aim for effectively zero methane emissions by 2030. So that goes beyond government level targets at COP26. Clearly, this space is moving very rapidly, and the world has woken up to how important methane is as a greenhouse gas and what we as an industry can do about it. And that's where measurement comes into the equation, because as every good engineer on this call knows, what gets measured gets done. The reason that we're measuring is not about having more accurate reporting for the purposes of things like sustainability reports, although of course that is important when we're dealing with our stakeholders and our shareholders. But it's by moving away from generic emission factors where it's effectively equipment counts to detailed measurements of the sources and the magnitudes of methane that are produced by our operations, that then we can focus resources and we can focus efforts on those parts of the value chain where we can make credible differences and intervene in a structured way. And where we make interventions, we can show and demonstrate those reductions in a defensible way. So as an industry, we can show progress, and we can show that our progress is making a difference. And in a world where methane comes from lots of different man-made sources, that matters. Now, at this point, it's worth bringing in some general terminology when we talk about methane emissions. You will see people talk about what are quite loosely called bottom-up and top-down measurements. When we're talking about bottom-up measurements, we're effectively talking about the values that find their way through to things like the sustainability reports. This is an aggregation of all the different sources of methane emissions as we understand them on our facilities, measuring them and bringing those together into a singular figure that is reported externally. When we talk about top-down measurements, we're talking about a verification and an additional step that is brought into that measurement process to provide the assurances to the people that look at those figures that what is being presented is accurate and complete, that we're not missing something significant. And so in this regard, when we talk about bottom-up and top-down measurements, it would be far simpler in some ways to be talking about reported emissions and reported emissions with verification. The problem comes with this is when we talk about top-down techniques, is a lot of the time people associate the top-down process with being uniquely synonymous with an aircraft or a drone or a satellite perhaps. And actually, there are different ways that you can go about these top-down measurements. It's the role that it plays in the reporting cycle that matters, not the physical way that that data was acquired. So that's enough about setting the general scene and why methane matters. And this is just one slide that builds upon what Mike was presenting a moment or two ago about the CCOP sensor and how it's used within BP and with some of our project partners around the world as part of that approach. So as Mike said, this is a sensor that has its origins in NASA and in space exploration and things like the Mars rover missions. And without getting into the nuts and bolts of it, the critical thing about technology that has its origins in that kind of application is about having something that is lightweight, that is robust, and it is stable. You have an instrument that can be deployed flexibly, and bearing in mind that the atmosphere contains about 2,000 parts per billion of methane in the background concentration, it's not just about whether or not it can detect parts per billion levels of methane, but whether or not it's stable enough to be able to differentiate an elevation in that methane background that's a product of some industrial process or some other source. And so it's about stability and precision as much as it is about absolute detection limits. For those of you who are interested in what's inside the box, it's a laser-based technique, as Mike said. So you are emitting a laser light at a very particular frequency, and the methane molecule is excited, or the presence of a methane molecule is excited by that laser source, and it attenuates the signal somewhat to the point where it can be detected. And it's the difference between what's emitted and what's being detected that allows you to quantify. But what it also means is it can be packaged into a very small space. We're looking at a total weight of less than a kilo, which means that it can then be used in a variety of ways. And as I'll show in a minute or two, it also means that you can move that sensor between vehicles. Because when we talk about methane measurement, we need to talk about a method. And a method is the combination of the instrument and how that instrument is deployed. And it's all of those things together that then go into the final value. So we now look at some use cases within BP of how we've used this sensor technology. A lot of the push around methane reductions has its origins in the US, and in particular into the onshore US market for oil and gas production, what was called unconventional oil and gas not so many years ago, but is feeling fairly mainstream these days. And with a large number of small distributed assets covering large areas of land, most of which do not have a permanent workforce attached to them, there is a significant challenge in identifying when a component is not operating as it should. And that is why a significant amount of the methane emissions from these type of operations are synonymous with the leak detection and repair program. Because left unchecked, a single valve, a single component, which isn't under direct supervision 24/7, could be emitting methane for many hours, many days, many months potentially. And that's why LDAR activity is such a critical part of what that particular market has to do. Now, I'll be honest and say, this is the part of BP that I have the least engagement with, because in the case of BP, our onshore US business is a subsidiary. And so they're largely autonomous in this space. But when we look at LDAR activity, there are two challenges. The first is to identify the source of the gas, and therein lies a whole host of different technologies, of which things that quantify the methane plume in the air are just one of the many technical approaches to spotting which valve amongst many hundreds potentially is the source of an emission. But then the second part of the equation is not just whether or not something is emitting methane, but how significant is that? How urgent is it to prioritize? And that's where quantification comes into the fore, because it means that you can look at hundreds of different equipment groups and, by whatever means necessary, work out which ones require human intervention, because it takes a long time to get between these sites. And that's also where the drone technology is significant, and why drones have played such an important part in the US market, because the time spent moving between facilities is greater than the time it often takes to do the measurements themselves. And the drone accelerates the speed at which people can move about in order to optimize their workload. And that has a significant safety element to it as well. So what you can see on the right-hand side of this chart is some work that Seekops did with my colleagues in the States, where they moved between 25 sites over a couple of days. And that's a detailed survey of each of one of those sites. To do that with a team in a truck with handheld type technology would be much slower. It would be a lot more complicated. And so that is where the combination of an accurate sensor, quantification, and mobility come together into a singular solution. Now, you can take that philosophy though and start extending it to the sites which I am more used to dealing with, which are both our large onshore and offshore facilities. And if we start in an onshore setting, BP has a number of large onshore facilities, gas processing sites around the world. What we can see on the slides is data from Oman and data from Azerbaijan. The Oman data was our first inroads into working with Seekops for a large onshore facility, and it was the first time I think that Seekops had stepped outside of the US into these kind of large centralized facilities. And we did two things. It was the first chance to look at as a total site and see whether or not the sum of everything coming from that site was accurate. In the case of Oman, it's a relatively new facility and there's very few sources of methane, and it helped confirm that to us. But it also allowed us to investigate in more detail the accuracy of individual sources. So what you can see on the top left is where we are flying the drone, or Seekops flew the drone downwind of the flares. Well, we know the flares are a source of methane, so it isn't a matter of find and fix. It's more of a matter of understanding whether or not the flare is burning efficiently. And we can do that by comparing some of the results from the sensor to the metered emission rates that we were reporting against for the flare. We can also, though, extend that capability to other sources of methane on the site, which were less well known. And what you can see in the bottom left is for the produced water facility. And this is significant in as much that we only found a small amount of methane coming from the produced water facility, but there should have been none. And having identified it, it sort of triggered the repair work that then went out and made the modifications. But you wouldn't have seen that source of methane using the technologies that you usually use for leak detection and repair, because it was diffuse over a relatively large area. And so the sort of optical gas imaging type methodologies that we use for leak detection and repair wouldn't be able to see it, whereas quantifying what's in the atmosphere could. Move ourselves forwards to 2021, and we took this technology and the requirements now to start doing these top-down measurements to one of our largest onshore facilities in Azerbaijan, a site called Sangashal, which has a whole host of different gas and oil processing equipment. Now, for those of you who are either out there or know that part of the world, it's complicated, and the weather patterns are complicated. And a combination of a complicated site and a complicated weather patterns means that the best way to work out what the total emissions from that site are is to break that site down into a whole series of equipment groups and build up a data set for each one of those equipment groups and aggregate it up into a singular value that we can compare for what we would have reported. And that means we don't have to worry about the fact that the wind direction changes every couple of hours, because the pilot flying a traditional drone has the flexibility to work the site over a couple of days to build up that sort of composite picture. And in doing so, they provide insights into how things like the flares are performing. And again, a bit like what we found in Oman, helped us hone in onto those pieces of equipment that maybe have smaller amounts of methane emissions, but shouldn't be there at all. So, you know, where you've got a valve or something like that that needs an intervention. And you can aggregate it all up, but while still being able to differentiate the large known sources like the flares from some of the smaller ones that maybe are less well known. And if you try to aggregate all of the emissions from that site using something like a manned aircraft flying a couple of kilometers away, you lose that spatial resolution. You lose the ability to differentiate the large things from the small things. You just see the sum of it all. And actually being able to see that granularity of data has value in terms of using the measurements to drive a reduction, as well as using the measurements as a way of verifying what goes into reporting is accurate. Now, the problem changes somewhat when we move to an offshore setting, and with an audience which is based in the North Sea. This is probably the operating environment which is closest to what most of you know. And in an offshore setting, we can throw some other complexities into the mix, not least of which being that there is a finite number of people that can be put onto a facility at any given point in time. And to conduct these top-down measurements, these verification measurements, you want them to be as independent from operations as possible, so that there is, you know, one measurement is done wholly independently of the other, and then you can compare whether or not they match up. And that's where one of my colleagues in BP did the matchmaking thing of, at the time, we'd been working quite closely with Seekops from a sensor and what is, I suppose you would call it, a traditional drone these days. And that's the sort of work we showed in Oman. But at the same time, we were also looking at fixed wing aircraft for other applications, you know, things like sending out emergency pieces of equipment and things of that nature. And it was my colleague who kind of said, you know what, we could do something quite special here if we put that drone, that autonomous aircraft that can go long distances and fly independent of what else is happening around it, with this sensor that has the accuracy in order to provide methane emissions. And that's how the partnership between Philogix and Seekops was born. And it's one of those sort of fortuitous comings together, which has produced some quite considerably, move things forward a lot in a very short period of time. And we can do that because you have a sensor which remains accurate at 250 to 500 meters away from the offshore facility, with an aircraft that is capable of flying with normal sort of civil aviation type rules, and then into a very tight formation around the facility, so that we can fly a series of orbits around the facility in very tightly managed sort of 10-meter increments up the side of the facility to give you the total quantified value and compare it to what we would have reported for that moment in time. And I'll show you some of the results from that in a moment. But in order to do that, we have to be absolutely confident that the combination, the method of the drone and the sensor, that we know exactly how well it's performing and can demonstrate to the emerging external regulators which are entering into this space that what we've measured is accurate and precise, and that the uncertainty of the method is well known. And in that respect, moving this combination of technology into something which is more akin to what you would do for other atmospheric emissions, like NOx emissions, for example. And the best way that we can do that is through a series of controlled release experiments where we know exactly what's gone into the atmosphere, and then we can compare it with what the sensor would do. And as part of a joint industry project that took place last year to develop this basic methodology, as well as flying out to a whole host of different facilities, and not just BP ones, there was 6 different companies working together through the auspices of the NZTC, the Net Zero Technology Centre, based in Aberdeen. By working collaboratively, accelerated the basic measurements in the field, but also gave us the resources to do this controlled release work in anger. And the way that we did that was to organise for some very carefully metered releases of methane into the atmosphere, and took a series of different drone flight formations, fixed wing, rotary drone, different flight patterns, and flew it around that release point that was off a very tall crane based on an airfield, and allowed us to demonstrate that the metered release rate and the measured release rate fall along a predictable calibration curve that means that we can demonstrate the accuracy of the technique and also know the uncertainty to it. So let's bring all this together into some real measurements. And towards the end of last year, building off the back of that NZTC program, we did a first sort of full-scale dummy run of what it would take to do one of these top-down verification measurements. So this is where we need to compare with what we would have reported for an offshore facility and do an instantaneous measurement in the field and compare it to that to provide that verification. And the instantaneous bit is important because, as anybody that's looked at emissions from large facilities, they're not stable, or at least they're not constant. You have long periods of relative stability interspersed by sudden changes in emissions intensity brought about by things like flaring events when a piece of equipment doesn't work or something of that nature. And so you can't compare your reported value that you put for the whole year to an instantaneous moment in time, because you don't know where in that distribution your emissions were. You have to be able to match what was happening on the facility at a given moment in time to what was measured in the atmosphere at a given moment in time to provide that verification. And you also have to put into that mix your understanding of what the principal sources of emissions are. And in this particular case, this is one of our assets west of Shetland. The majority of the methane emissions, as we understand it today, come from flaring, about 80% or so. And of the remainder, about 10% comes from fuel gas. So this is from power generation. And only a relatively small proportion comes from fugitives, from methane escaping through flanges and valves and the like. And so the exam question in that regard is very different to what you might have seen in that onshore US setting that I was talking about earlier. and over 90% of our emissions are metered. That's what goes into our reported value, but we still need to verify it. And so coming into November of 2021, we conducted 3 flights over the facility over a weekend period. And we only flew over the weekend so that we could separate our work from essential helicopter flights. And we're able to compare what we would have reported over those 2 days to what we measured in the atmosphere for the same moment in time. And that's what we can see on the next slide. Whereas if you take our metered sources of methane emissions, our flares and our fuel gases, and aggregate them all up, we are reporting something in the order of 20 kilograms per hour of methane released to the atmosphere. I cannot stress enough on these calls that 20 kilos an hour is a very, very small amount of methane. There are plenty of examples in the literature of individual pieces of equipment, individual components capable of releasing significantly more than that. So the exam question is really rather difficult. You've got very little coming off the facility, but you're still required to verify it. But flying at 250 meters from the facility and taking orbits with an aircraft that was capable of flying to a very tight formation and a sensor on board capable of measuring very small shifts in the concentration of methane, allowed us to produce a verification measure of 17 kilos per hour. Now, obviously 20 and 17 are not exactly the same, but to all intents and purposes, they're statistically indistinguishable. And that means that we can say with confidence that our reported value on that day is accurate. And not only is it accurate, but that facility is actually releasing very small amounts of methane. And in a world where methane matters and where the future of these large facilities matter, providing people confidence that what we're doing and what we're reporting is fair and true is really critical to being able to demonstrate the longevity of these assets. One of the things that's built into agreements such as OGMP 2.0, though, is a spirit of continuous improvement. And yes, 20 and 17 are pretty close to each other, but they're not exactly the same. And so we don't stop here, and we should feed these results back into our planned measurement program for 2022. And we do that in 2 ways. One of the ways is to say, is there something in our reported emissions that we don't understand that creates more fluctuation than we would be reporting? And we can do that by investigating in closer detail what's happening with the power generation and with the flares to understand whether or not that's a source of fluctuation. And we continue to work with Seekops and Flylogics and industry peers in pushing our understanding of these top-down techniques to understand whether or not the uncertainties of the method need further refinement. And it's only by coming at it from both directions that what we do will benefit not just these facilities, but then allow us to translate this know-how to other parts of the world as well. So I'm mindful of time, and I'm mindful that I talk a lot, but that's probably a good moment to sort of pause and see, Alex, if you've got any questions on the line or anything that people would like us to clarify.
Great, that was excellent. Thanks, Peter. Really interesting talk and invaluable to hear BP's perspective and operators' perspective as ever. It's really good. And I guess the obvious question that springs to mind really is how are BP going to progress with this technology? Metaphorically and geographically, where are you going next?
So, arguably the most exciting thing that we'll do in 2022 is the North Sea region will do a full-scale dry run of these verification measurements for every facility that we operate. So in a couple of weeks' time, we'll start in the west of Shetland and then work across to the North Sea. And that means that by the time we get to the end of 2022, we will have looked at every facility we operate, everything that we would have reported for those facilities, and hopefully verified those emissions with sufficient measurements on each one of those pieces of equipment to satisfy everything that's coming out of things like the OGMP 2.0 requirements and what's coming out of the EU. In terms of technology development, though, the other exciting thing that we're keen to do is at the moment, when we fly on these offshore facilities, we have a spotter. We have somebody on the facility who steps out of their other duties and watches the aircraft doing its orbits for about 45 minutes, just as an added tier of risk management. That's fine, but we operate a number of sites around the world which are normally unmanned. Yeah. And we're keen to continue to develop the risk assessment processes that we can, where we choose to, eliminate the role of that spotter, which means that we can take measurements in a far more diverse range of facilities, but also with much less forewarning that the measurement is going to be taken. We're going to do some of that in Trinidad, where we have several of these unmanned installations. But it also means that we're moving towards a position where we can do routine measurements. But if we have a period of plant upset with elevated methane emissions, we can scramble the methane measurement technology in order to get some really accurate data at the moment in the year that really matters for a facility. And in order to do that, you need critical mass of different people using these type of measurements to make that on-demand type application more accessible. It would be, most of the emissions that happen offshore occur for like 12, 24 hours tops at a time. Yeah. It wouldn't work for me to phone up Mike, who's got most of the team based down in Southampton in England, and say, well, can you drive all the way up to Scotland and then start getting in place the measurement systems in order to cover off some of these unplanned events? Having permanent bases and permanent capability moves us towards that level of measurement security where we can call on it on demand and as part of a routine service. And all of those things, I think, are super exciting for 2022.
That's really interesting to hear. And sorry, I'm being a bit selfish here. And we have got a question there waiting, but another question of my own. Quickly, I'll get in with it whilst I can. The environmental angle on it had always been obvious to me, but I hadn't quite appreciated the business case. Like in a remote environment like the Permian, where you could actually identify a leaky wellhead that you didn't know about. So you've obviously got the environmental benefit of detecting it, but yeah, if you're losing gas, then you've got a commercial angle on that in terms of revenue that you recoup through gas that you've not lost, as well as minimizing any damage to equipment potentially as well. And has that proved valuable?
I think in things like the onshore setting, the EPA did some fairly detailed work of the cost-benefit analysis, particularly of swapping out things like high bleed pneumatics, because there's a payback there in terms of the value of the gas. But the other thing that we're starting to see the emergence of is differentiated gas, where people that can demonstrate that their gas production is inherently low in terms of its greenhouse gas emissions will either pass various trade tariffs, which is what we see being set up in the EU, or be able to sell gas at a premium because their gas is demonstrably lower emissions. But you can only do that with good, accurate measurement data.
Yeah, that's interesting. Thanks. And I've had Mike asking some questions. John, what have you got there?
Yeah, sure. So great presentations from everybody actually. So thanks for that. I'm delighted to see actually I've got one of my old lecturers, Babs, on online as well, and he's asked a question, and not a challenging one, but in two parts. So I'll perhaps open up one question to each of you, Peter and Michael. So the first question is, does the sensoring technology differentiate between methane and CO2? And secondly, for the definition of composition for methane, does that accurately sort of assess water vapors present within the methane itself? So two questions. Perhaps the first one with regards to differentiation between methane and CO2. Is that something that you can answer, Michael?
Yeah, so the sensor that we have today just measures methane. It's designed purely to mention, it's tuned to the frequency for detecting methane. We are actually working on modifying the sensor so that we will be able to measure CO2 as well. So that's an ongoing development project at the moment, and we expect to trial that sensor later this year. So that is, obviously there's a lot of interest around that in the industry, so that is something that we are working on, and it will be based on the same physics, if you like, the same type of laser, but it's a case of there's obviously some modifications that need to be done to make it suitable for CO2.
Excellent. Peter, perhaps you could, is there any thoughts you have on the composition of methane?
It's actually really good to have somebody from the academic world raise a question on this, because everything that we do, why we do stuff about methane and how we go about doing atmospheric measurements would not exist were it not for the research grade instruments and the research aircraft that did most of this groundbreaking work. But what is fit for purpose for research is not necessarily something which can be readily deployed at scale over a large number of assets, because there's a finite number of aircraft, and those instruments are really, very sensitive beasts. We need something which is a bit more routine, which is what we're really talking about here. Having said that, the very light sensors, as Mike was saying, the ability to potentially differentiate between methane and other hydrocarbons to do the methane to CO2 ratio are natural progressions on the technology journey for this type of capability, as is the ability to use these type of methods for not just doing the oil and gas sector, but do the oil and gas sector and things like landfill sites or urban areas and all of these other things as well, where doing methane ethane ratios, methane CO2, all of these things add to the global understanding of what the sources of greenhouse gases are. But in order for a technology to get to all those different applications, you need that first killer app. And that's why it's been so important that the oil and gas sector takes a lead in this, because we don't need everything. We don't need the totality of what's possible. But in developing the technology for the oil and gas sector, there will be a trickle-down effect where that technology becomes more accessible, more robust, more affordable, that it can be used by all these other sources of methane as well. To the point being where you then start getting really complex situations where you've got oil and gas facilities juxtaposed with other urban sources of methane, with agriculture, and you need to unpick all those signals. And we'll get there eventually, but at the moment, it's just around the methane measurement.
Okay, no, I think that's a very good point. And I guess, so almost to follow that up, when we look at the sensor and the types of technologies, I guess it'd probably be a similar answer, but Adrian's asked a question with regards to, so hydrogen. So now that, there's this kind of discussions about hydrogen having that global warming potential as well in comparison to CO2. When we're looking at these new hydrogen developments that are happening, do you see a potential or a market, or is there current work being undertaken where you're looking at similar sensoring technologies for the detection of hydrogen slip and hydrogen leakage?
I think there's two parts to that, isn't there? Hydrogen clearly is another one of the gases that will play a critical role in the energy transition. In order for it to fulfill its potential, we need to have the ability to measure emissions from a greenhouse gas point of view, because as you know, it has a global warming potential of its own. But also, in terms of technology pathways, the other thing we've got to be mindful of is hydrogen is not an easy gas to work with. And there are sizable safety considerations that need to be built into the emergence of hydrogen infrastructure as well. And on both those counts, having methodologies for measuring hydrogen emissions to the atmosphere will become important. The fastest way we get there, though, is arguably by getting good at the gases that we're used to dealing with, like natural gas, and then building on it into other parts of the value chains.
No, absolutely. I think it's one of those areas where it really kind of there's a natural, sort of linkage, and I think the system will have multifaceted as things progress and continue. And I think the lessons that we're learning now will transcend into other sort of gaseous mediums that we have. So I guess, Alex, I've dominated the questions here at the moment. Is there any questions that you've got? I got a couple here, but I'll pass over to you, see if there's any questions you have at the moment.
No. Thank you for holding the fort whilst I had a bit of a coughing fit. And just to remind everyone, we've got a few minutes, so please post any further questions in the Q&A. Sorry, if you've got some more, John, go ahead.
Well, one of the questions I kind of thought about when I was looking at the presentation, Peter, is the fact that you had your reported values versus your actual, and so the actual is actually less than what would generally be reported, and that interested me, because I would have thought it would have been the other way around, that you perhaps would initially underreport. So I guess, are you noticing any trends at the moment between what's generally reported based on estimates and what's actual, or is it too early to say at the moment?
So I think the first thing I'll say is you've got two different measurements, and what we're doing with the Seekops type technology is a verification, not a validation. What it is it's independent. It's not better or worse. So all you can really do is, providing you understand the uncertainties of your two methods, you're looking for a good match, a good statistical match between the two values, but you're not intrinsically saying that one measurement is better than the other. They're just different. So when there's a slight offset between them, it might be just statistical noise. It might be something more physical. The reality is 20 kilos, 17 kilos, that's so low. On a global scale, I cannot begin to emphasize just how low that is compared to methane emissions you see from other operations in some other parts of the world. So, but then there's always stuff that you can learn. And one of the best things that I've seen come out of the guidance that bodies like OGMP has written is not to say, here is a perfect method, this is exactly how you have to do it, and this is how it's going to be forever. But here is some guidance on how to take measurements, but learn from them. And the more measurements that people learn, the more we'll start to learn whether or not, where these discrepancies are real and whether or not they are consistently being held. And pooling data then becomes really important. That's what the UN's tried to set up with this thing called the International Methane Observatory. But also, in credit to a lot of my colleagues in the North Sea, the work we did last year with the Net Zero Technology Center, we learned so much more by collaborating than any company could have done working individually, because we wouldn't have been able to do that number of flights. Mike, if I remember correctly, I think it was 17 flights were done in the North Sea last year, something like that. Yeah, I mean, it was a sizable number. And every flight was built upon what was learned from the one that came before it. And so that sharing of information, that transparency will then reveal whether or not, as an industry, where we've been systematically high, where we've been systematically low, and all of those things then go into the reduction plans.
Okay, John,
Mike, did you want to elaborate on North Sea campaign last year. Were you just going to say a few words on that?
I was just going to add, just to add to that, yeah, that was across 6 different operators collaborating on that. So, and a variety of different assets, from platforms to bridged facilities to vessels as well. So a variety of assets and across different operators. And I think, you know, having that operator group all working very collaboratively together was absolutely crucial to the progress that's been made over the last 2 years, really, that this project has been going, with the support of NZTC as well. That's been absolutely critical.
Great.
I guess one last thought for myself is just you know, now that you're talking about flights and that, for when you consider from, I guess, an asset integrity perspective for methane emissions, how often, you know, is it looked at that these flights would take place on a specific asset? Is it, you know, is this a monthly thing, annual thing? How is it being predicted at the moment?
You've locked onto what is probably the single biggest topic of discussion in bodies like OGMP at the moment, of how many is enough. I mean, you know what? I think the honest answer is I don't think anybody knows. And I think it goes to the spirit of the question that you gave a moment before, that we're on a journey of exploration with this. And if we were to lock into a very precise number of measurements at this point in the cycle, the only thing I can guarantee is that number is probably wrong. So what we can do is we can learn and then modify the plans accordingly. So in the case of BP for this year, when we do the work in the North Sea, the plan is to go to each facility twice. Is there anything deeply statistical meaningful in why we're going twice? No, just that twice is better than once. And we will learn from that. And then we will learn how many flights are required to really get a feeling for an understanding and feed that back into the guidance documents. I suspect that there won't be a singular number, that it will be done on a risk basis, and facilities that show greater variability in their emissions or higher levels of emissions probably should be measured more often, but exactly how many times more often, time will tell.
Perfect.
Great. Thanks, Peter. Thanks, Mike. That's 1 o'clock now, so it's time to draw things to a close. I think that's well, yes, suitably prompt timing. So, yeah, great. Big thank you to both of you, Peter, Mike. A really interesting session on a really hot topic. And just to remind everyone else online that we will be able to make the video and the slides available through the SPE Aberdeen website and the YouTube site. So check back in there or follow us on LinkedIn for updates on that. And so, yes, thank you very much again, and see you next time, everyone. Enjoy the rest of your, what is a sunny day here in Aberdeen.
Thank you.
Bye-bye.
Bye for now.